EPWM module consists of a time-based submodule, counter compare submodule, action qualifier, and then we have chopper, deadband, trip zone, event trigger, and digital compare. So from this submodules, we saw that time-based submodule is a 16-bit counter, and time-based counter is there, and it goes on increment and decrement and gives you output as a triangular way. And then we have a counter compare register, which is there in order to store your steady state value, digital value. And in that case, if you have a constant straight line, okay, so that straight line will be there as a counter compare. So that will be comparing your triangular wave, and based on that, action qualifier will set certain particular action so that your EPWM pulses will be on and off. And then we saw how to trigger the phase shift by using TBPHS resistor. So by using TBPHS, this was about action qualifier resistor. So you can see in action qualifier resistor, there are 16 bits, and bit number 0 to 1. If you assign 0, 0, it means what will happen over here, that is shown. So you can see if you put 0 in this particular bit, it will start triggering on 0. Other bits in this case should be 0, and this 0 1 bit should be 1 only, so that your counter will start at 0. Similarly, you can program this register, okay, and you can see key what your action qualifier is assigned to do. Best way to look into this is through the technical reference manual, as it won't be confusing. You can go to technical reference manual, and from here, if you go to EPWM and action qualifier submodule, so from action qualifier submodule itself, you can see what are the registers available to you. So the end of this particular EPWM module, yeah, I think somewhere here. So here actually detailed explanation will be given for each and every bit, that if you put 1 into that particular bit, what will happen, if you put 0 into that particular bit, what will happen. So you can actually do it like this, and this was about synchronization of output that we saw, sync in and sync output. So through instruction, it was little bit easy as compared to looking over from this particular data sheet. Okay, through instructions, which actually given you all the examples by TI, it will be easy for you to program from there. And then you look over here if you want to program something else. So these registers will be there. Okay, so we saw about EPWM three modules like time-based, counter compare, and action qualifier. Today we'll see about deadband and PWM chopper, and trip zone I will teach later. Event trigger, we saw how to trigger an interrupt using event trigger. That is so this session will be little bit short, and evening session will try to take more time, because evening most of the people are free. So so I guess everybody has not watched all the videos. Okay, so I request you that you watch all the videos first before going through every exercise. Okay, because each and every video I have told you what to do. Okay, so it will be easy for you. So we saw this code yesterday, how to initialize PWM modules. Okay, and how do you see that your triangle is generated? You can see from this one that I think someone has came. Just hold on for a minute. Yeah, so we saw this that yesterday. Mm, there are certain variables that we have assigned. to comparator register, time-based period register. Then there was a structure where we defined certain inherent variables, which are unsigned integer 16 bit. Okay, and which will be, I mean, these values will be ranging from 0 to 2 to the power 16, as we saw yesterday. Then there we suggested one pointer known as EPWM register handle in order to take care of all the variables that are there into this structure type of variable. So in this one, then we saw how we can declare the functions. These are our function prototypes, global function prototypes, and these are the declaration of the functions that we saw why it is necessary, as some of there are in header file. If you are defining your function on your own, then you have to declare it somewhere here like this. So 6 to 7 functions we are using into this code, so they are defined over here. And then we saw the procedure for main code using system control, peripheral clock, EPWMs, and how to trigger interrupts. We are well aware of that, and how to take particular ISR, how to call particular ISR from pi vector table. So this is the instruction for that particular thing, and it is mapped to your ISR function, any call of any interrupts. Okay, so after this we saw how to synchronize all the EPWM module. That is, this particular instruction of time-based clock synchronization is used for synchronizing all the EPWM modules together. Then uh, then we saw about that whenever our interrupt is executed, it is executed with the help of event trigger selection register. And we saw that I forgot to tell you yesterday that whenever any interrupt is occurred, first you have to clear that interrupt flag so that your IFR bit becomes 0. So this event trigger clear register will clear the interrupt from that particular bit which is occurring, like EPWM 3 from here. And after that you have to acknowledge the same interrupt, like group 3 interrupt, so that your interrupt keeps on receiving. So as we saw yesterday, acknowledge is like thanking, so that interrupt should occur again and again. You can understand it like that. And we saw the event trigger register as well, that your interrupt selection, where you have to select your interrupt to occur, whether it is on 0 instant, period instant, comparator A up instant, comparator B down instant, it's your selection completely. So in this interrupt selection register, you can select any one of the event from here. After that, this is an interrupt enable, which we saw yesterday, that you have to put one over here in order to enable your interrupt module through event trigger. So event trigger is basically extending the capabilities of your Pi module so that it should trigger interrupt on particular event. And then you have a period of interrupt selection, that is for after how many triangles of your time-based period your interrupt is generated. That is, we have assigned it on third one. So I guess till here nobody had any doubt, and we saw that how particular interrupt we are taking into account in order to vary our comparator, so that our comparator should move up and down, and how its value is increasing with comparator plus plus with this particular pointer which is in the arrow direction. So EPWM info is accessing everything with this EPWM register handle pointer, and it is pointing towards the beat of comparator, and then we are incrementing it by 1. And a certain condition is written over here, that if your comparator is greater than maximum, we ask comparator to go down. If it is less than minimum, we ask it to go up. So that condition is there into this particular block for comparator A and comparator B. So this was the example which is given to you in order to you know try to write your own algorithms. So what you can do whenever you are practicing, you can just copy this code, okay, and you can take your text file. So into this notepad, you can paste your code. So whenever you want to change anything into the code, you can easily change it from the text file. And when your changes are done, you can paste the same file in here. So in that way, you can modify if any content is there. Okay, you can as well see if any errors are there during building by then, and you can change it. So whatever codes you write, you try to save main file into text file. And as you all know, APIs we saw how to create, and generally they are into their C2000 device support only. So you don't have to create APIs on your own. Otherwise, it will show that you have redefined the APIs as they are already defined in C2000 compiler. Okay, so all the drivers and everything it's over here. And whenever you are trying to generate any code, we saw through Resource Explorer that you can implement. Since my board is not connected. . So this we saw yesterday. So this was about the revision. And phase shift we saw that if you put your time based counter value equal to TVPHS, automatically your triangle will reset at that point of time, and then your phase shift will occur. So in this way you can generate the phase shift. You can imagine your triangle will start from here itself after that, so that your comparator, whenever it is comparing with that particular signal, it will generating the phase shift. Okay. And then we took the exercise. So from this example you can see I have put certain value into TBPRD, and I have put phase as 0. I have said here 04E0. If you convert this into binary, you will understand that TBPHS bit is assigned to what value. So from here the phase is 0. So comparator I have set it at half the values of TBPRD. So my 50% duty will be there, and my PWM which will be generating, it will be of 50% duty cycle. So if we have scope also, we can see with this. And when you receive your board, you try to change this bit and try to measure your duty as well, how it is coming when you are putting your comparator values. Okay. So it is like that. And so this was about PWM module. I will look into little bit about deadband and PWM chopper. So deadband is something which offers you, like let's say whenever you have an inverter, everybody is well aware that an inverter. So whenever we see any edge bridge inverter, so from this edge bridge inverter, we know that we want some phase shift, we want some dead band into S1 and S4. If that is not so, what will happen is, if S1 and S4 are on at the same time, then the DC link capacitance which is connected over here, it will get shorted. And as you all know, IGBT has a longer turn off time than turn on time. So it takes longer time for any switch to turn off. So when this switch is getting turned off with little delay, you don't want this switch to be on at the same time. Otherwise, there will be short circuit over here, and it will cause a huge current to flow through your DC link capacitors. This condition we call it as a shoot through condition. So in order to avoid that shoot through condition, we give dead band in between these two switches, so that before turning on of S4, your S1 should be off. So that dead band, you can give it into this particular microcontroller with some logic, and that logic diagram is shown over here. So basically, there are actually, these are the modes of deadband. This upper signal is EPWM 1A signal, below signal is EPWM 1B signal. So you can call it as output A, and another one will be output B. So from here you can see what I mean by rising edge delay is, sorry, this one is rising edge delay. So if your output is something like this, and you want to give rising edge delay, so that your rising edge will come with certain delay, and your falling edge will be at the same instant. So you can put rising edge delay, or you can put a falling edge delay, like your waveform will start at the same time, and you can turn off switch S4 after a certain period of time before turning on of switch S1. Okay, so in this way you can delay turn on and turn off of any particular switch. So there are four modes of this. One is active high complementary, active low complementary, active high, and active low. So in this mode, you can see EPWM A and EPWM B are totally inverted, in which EPWM A is there with certain rising edge delay, and EPWM B also has certain falling edge delay. So active high complementary means EPWM 1A will be totally inverted as that of the EPWM 1B. Then you have active low complementary. In this active low complementary signal, your EPWM-A will be active low, you can see here, and EPWM-B will be active high. Then active high, in active high mode, your EPWM-1A will be high and 1B will be also active high. In the active low mode, you can set EPWM-1A as active low and EPWM-1B as well as active low. So you can select any one of this mode. Okay, where let's say if you have generally your S4 switch is inverted of your S1 switch, I guess. So in this active high complementary mode, you can see this facility is available, in which your EPWM1A will be in the positive way, where your S1 will be on, and in this case your S4 will be off. So you can use this mode as well. So whatever mode that you want to have, okay, as per your requirement, you can set into this. I don't know what circuit you are operating. So If your waveforms are like that, if you see PWM on your oscilloscope, okay, then you can decide that what delay you want to keep, what deadband you want to keep. Okay, generally in any gate drivers, if you employ Skyper 32 gate drivers, if you look into Skyper 32 gate drivers, so if you employ this kind of gate drivers, it is suitable for switching frequency up to 20 kilohertz. Okay, you can't go beyond, I guess, 40 kilohertz. It is the IGBT, SI IGBT. You can switch easily with this particular microcontroller. You can switch SIC as well. Okay, but that needs to operate below 40 kilohertz frequency. So you can use this gate driver. This is power module of that gate driver, and this is the another extending. You have to fix this power module onto this particular board. Okay, this holes over there, black holes are there. You just have to put it over here, and you have to insert certain resistances. So with this module, there is already inbuilt deadband is there in order to prevent your short circuit or shoot through condition. So that protection is also there into this gate driver. So in that case, you don't need to do it in software, but if you want to have extra protection, you can do that as well. In your deadband, you can try to see. So when we'll see our code, we'll see how actually it is. Okay, so what is the time that you can set for this particular thing, and what are the modes for selection? So there are basically uh, two resistor. One is rising edge delay counter, another one is falling edge delay counter. So in this counter, you can select your deadband mode to this particular switches, that is S0, S1, S2, S3, and other modes are also there. Like if you want to bypass certain EPWM and you have to give delay into EPWM only, that you can also give. Like you can see in mode description, if your S1 and S0 are 00, and whatever you put into this deadband control polarity selection S2, S3 bits, okay, your EPWM and EPWM will pass with no delay. So you won't have any delay into your EPWM and EPWM. So whenever you are implementing any deadband and you don't want to have a deadband, you can put it like this. In active high complementary mode, that if your PWM signal something like this and your PWM signal is something like this, and in that case, if you want to give, if you want to generate that kind of thing, you can use polarity selection as 10 and output mode as 11. Then you have active low complementary as we saw over here. So you can put these values. We'll see in code how to put these values and what kind of modes you're getting. Okay. After that, you have polarity selection and output mode with the help of S0, S1, S2, and S3. So you try to understand this logic through this particular bits that is shown over here, this particular diagram. It's showing that if you click your S4 to 1, it means you will have, if suppose this is PWMA, okay, it is coming through S6 like this, like this, like this, if it is coming, and then it can go to 1 as well, it can go to 0 as well. So if it is on to 0 and this bit is on to 1, okay, then your rising edge delay will be on, okay, and it will come through this particular line. And if SIT is 0, it will connect to rising edge delay block, and after that this has to connect it to PWMA again. So in this way loop will get completed. Okay, so these switches are there in order to design logic. You can see if this S4 is connected to 1, then your PWM okay, your PWM has rising edge delay. Similarly, input mode in S5, if you select this switch at 0, you can implement PWMA into falling edge delay mode. And if it is connected to 1, then you can implement PWMB into falling edge delay mode. So you have a rising edge delay circuit, you have a falling edge delay circuit, and these two circuits are used for both PWMs, PWMA and PWMB, with the help of this input mode. Okay. Then you have your deadband mode, like whether you want to bypass this any particular deadband. Let's say if this switch is connected to 1, okay, this logic is little bit complicated to understand. Okay, so that's why they have given output mode and polarity selection mode bits written over here, that if you put anything, it will somewhat happen like this. Okay, so in this way you can use any of the bits. Okay, I will explain this in detail, how actually you can do it. From here it is little bit difficult to understand. Okay, so once one by one if we see, Okay, let's go to technical reference manual. Exactly, you'll understand from there. Yeah. So these are the modes that I have shown you for operation. And these are the additional deadband operating modes. So from additional deadband operating modes, you can as well have facility to bypass particular signal like EPWM. In this one, if you select S6, S7 and S8 bit, which is for deadband mode and output swapping mode, if you put 000, both the signals are determined by output mode bits. Means it depends on output mode now what you are putting. Okay, if you are putting 000 into swap and this particular deadband mode, then your EPWM A and EPWM B will be decided by output mode. Okay, if you are putting 001, it means EPWM A will be defined by output A modes, like output mode bits. Whatever you put, EPWM A signal will be based on that. Okay, but if you are putting like 001, your EPWM B will have path that will be defined by rising edge delay or delay bypassed. like uh, like you can only introduce rising edge delay or you can bypass the delay. You cannot introduce falling edge delay into this EPWMB after having this particular thing. Okay, so it's little bit tricky it will be to understand. I guess if you try to explain it through. Okay, okay, let's have a look into this as of now. Okay, once we'll see the code, we'll try to demonstrate it over the oscilloscope by putting every other bit, okay, into every other mode so that you can see PWM A and B signal. I think that will be more clear to you as compared to this. So one by one, then I will explain. So the time for this, any rising edge and falling edge delay is given by this particular formula, that is deadband FED, deadband RED. So these are the register in which you can put any value like 1, 5, 10, 100, any value you can put. And your time-based clock, time for time-based clock is what? As we saw yesterday, your time-based clock operates on 50 megahertz. So this time for time-based clock will be 20 nanoseconds. So 20 nanoseconds into 1. So whatever you are getting, that will be your falling edge delay. Then you have 20 nanoseconds here, and if you are putting RED as 1, your falling edge delay will be 20 nanoseconds, rising edge delay and falling edge delay. So depends on your time for time based clock and your these values, your rising edge and falling edge delay will be there. Okay, is this clear to everybody? Okay, so this was about deadband, and we'll take a code of that. Okay, first I'll talk about PWM chopper. So into this PWM chopper, you have two PWM signals, A and B. And what does PWM chopper does is it chops your PWM A or B signal into low frequency, sorry, into other high frequency signals. Like you can see, these A and B are low frequency signals. Okay, now you have a certain wave of chop frequency in which you can put frequency up to 10, 20 megahertz. And what you can do is you can pass this particular, you can logically add this chopper frequency to A and B, and after that your EPWM A and B will have output something like this. You can chop your PWM wave into small turn on and turn off interval with this PWM chopper. So if any application requires this, you can as well have this feature of PWM chopper. So there are certain registers like you can put it into the one shot mode. Okay, so how it will be like that. And okay, so how you can set your chopper clock frequency, like high frequency, that wave, chopper frequency wave, you can set it from this one. Whatever your system clock is operating at, like let's say your system clock is operating at 200 megahertz or something, and you can put frequency division value into that particular bit. We'll see in the program how to put that. So based on that, your chopper clock frequency will be decided, and your chopper duty cycle also you can adjust, like this is 50% duty. So if you want to change the duty of this, you can as well change the duty of your chopper signal so that your EPWM signal's duty will also change. It won't be in 50% mode. Okay, so this is the main register of PWM chopper in order to enable your chopping of your waves. So chopper duty you can set from a bit number 8 to 10. Chopper frequency you can set from bit number 5 to 7. And you have to enable one shot pulse width. One shot pulse width is what that we'll see. Okay, so you can see from this figure, you can see from this figure the period of the time for which your first pulse is on, that is called as one shot mode. So you can as well have facility in order to change the first pulse duration, turn on duration, that you can do with this programmable pulse. So this is a programmable pulse. Whatever value you will put into one shot, okay, it will have that particular on period. So you can operate it in one shot mode, or you can as well bypass that particular mode. Okay, then you have a chopper frequency that you can set, chopper duty, and chopper enable. Like if you put 0, it will be disabled. If you put 1, it will be enabled. Okay, so this is the formula for time for setting first pulse. Time of system clock out means 1 divided by 200 megahertz into 8 into whatever one shot width that you wish to put. Okay, that you can put over here. So it is based on this particular values. Okay, from 1 to 4, if you are putting 000, it will be 8 divided by 8 to your system clock frequency. So like this you can put. Okay, and this was about chopper and little bit about chopper and your deadband. Okay, once when we'll see the code and when we'll see the exercise, into that module we'll see return what is there. Sign PWM. This was the first code that I have written. So into this particular code, I have assigned certain variables like modulation index, clock frequency of CPU, with this DAC and everything that I will explain later. So certain variables I have assigned result as S2, S3 for my convenience. Then I have put sampling frequency TS. Then I have put omega naught fundamental 2 pi f to set that. You have theta 0, that is initial value of theta. In order to program your sine wave, these variables are required. So this reference 1, reference 2 I have put. Then these are all the float variables, like they can have as well as decimal values. That's what float means. You can as well put double. Then you can have, then I have put certain variables which are unsigned integer of 16-bit. And then I had certain functions like EPWM 1 to 6. Since I'm programming 6 PWMs into this example, I have written 6 initialize EPWM examples. Okay, so as per the procedure, first I have enabled the clock, then I have disabled all the interrupts, and I have enabled the peripheral clock. We saw this is a peripheral clock control register 2, in which EPWM 1 bit clock is on. Okay. Then I have initialized my PWM. This is the initialization of PWM through GPIOs. So these are the predefined functions. So 6 I'm using, so I have put here 6. Then I had a pi control register, and I'm clearing all the core interrupts from IR and IFR. Then I had initialized 5 vector table and DAC for my purpose in order to see the output. So once DAC section will be clear, you will understand about DAC. So this is what I have done over here. That in this one, it's one more thing that I would like to tell you is that you can as well divide your EPWM clock. Okay, if you put EPWM clock divider 1, okay, your clock frequency of EPWM will also decrease. Like if you don't want to have it at 100 megahertz, you want to have it at 50 megahertz, you can put here 1 as well. Okay, so this is also one register which is peripheral clock divider selection register. Okay, so many registers are available in technical reference manual like this. Okay, so this is not required, but if you wish to put, you can put it. Then it means that my EPWM clock is now operating at 100 megahertz. Okay, then you have a peripheral clock control register, time-based clock synchronization equal to 1. So it will synchronize all the time-based modules. Then I have triggered here timer 0 interrupt, that is CPU timer 0, and I have called an ISR, that is CPU timer 0 ISR. This certain arrays I have initialized in order to store my values of sine function. So what I have done is I have taken an array of 10 in size, and I have initialized it to 0, 0, 0 first. So I have taken 6 arrays here like that: A, B, C, D, E, and F, I guess. Yeah. So this is the instruction that we saw. We are calling interrupt at particular period of time. So I'm operating at 200 megahertz. Previously we saw example of 60 megahertz. So CPU frequency megahertz, you can see from here, it is set at 200. So I'm operating at 200 megahertz to my CPU timer. Then I'm calling my interrupt after this particular execution of this particular instruction. That is whatever value of INTRPT and into this. Okay, so after this time, my interrupt will occur. So let me check what is this. Okay, so I have put it here something like this. So as per my convenience, I have done that. Whatever sampling frequency to which I need to generate my particular PWM. So it should be higher than that, because whenever you are generating sine, you are generating it in a discrete way, that is sample by sample. So whenever you are generating one sample, you need to make sure that whenever interrupt is occurring, so the time duration between that two samples will be much more lesser, okay, than your sampling frequency or your sampling time. So from here, this particular instruction into TCR bit, okay, it's to start the CPU timer. Don't forget to add this instruction. I always used to forget to add this. So this is important in order to start your CPU timer. Then we have triggered an interrupt of group 1. M is enable switch we saw. This is belonging to group 1 and subgroup 7. And then we are turning on the interrupt. So this is the ISR in which I have written the code. Okay. So I have written 0, 0, 0 into TCR bit once again in order to reset my CPU timer. Whenever ISR is happening, once again I am resetting my CPU timer. Okay, so it's basically 1 over here, it should be 0. So here I'm generating a sine wave. Okay, so from here you can see your sine is basically of 2 pi, which is 6.28. So whenever another 0 comes, if your theta is greater than 2 pi, your initial theta will be assigned to 0. So this is the logic for generating sine. I'm taking initial value as 0, and then I'm taking it here as Ts into omega naught. So this is 2 pi f omega naught, and this is Ts is sampling time. So 2 pi f into Ts plus initial value, that will be my theta. So accordingly, my theta will update. And if theta is greater than 6.28, that is 2 pi, again it will go to 0. So in this way, one sine wave will be created. And then here I have used a function called as sine theta. So I have stored my values into org, where I am storing all the values of sine theta. So whatever sine wave is generating, it is stored into this particular org bit. Okay. Then I'm adding certain reference into this sine, because this sine will be from, I guess, -1 to +1. So I don't want it from -1 to +1, as my triangle into this TBPRD register, it will be starting from 0. So for that, I'm putting 1 into this sine theta, so that my sine will be now from not -1 to +1, it will be from 0 to 2. Okay, then I am initializing again theta 0 to theta, and then I am putting these values into AI so that I can see into the array what is the value of my sine signal. Okay, so whenever this kind of AI and reference everything is available to you, you can just put this into expression. Okay, we saw our expression window. It's something like this variables window. When you run your code, you can put into variables and can monitor the values of all the arrays. Okay, so it is like this. Then I'm putting comparator. Into this comparator, what I'm putting is, this is the sine. So I'm putting my sine into comparator, and I'm scaling it with respect to my TPRD, because my TPRD, if it is from 0 to 2000, and if sine is from 0 to 1, I will not be able to compare that. So I have to multiply it by 2000 in order to make that comparator equal to TPRD. So this way I can set my modulation index as well. Okay, this is the logic for setting modulation index into comparators. So this was about it. Then I'm phase shifting another sign with respect to 2 pi by 3, and another sign with 4 pi by 3. So this is for three phase. Okay, so three phase signal I'm generating here. okay, for a three-phase inverter to operate. So in three comparators of EPWM 1 and 2 and 3, I'm putting three sine waves which are 120-degree phase shifted, okay, and that I'm comparing with the triangle. Let's show you in a particular way. So this is like what I'm trying to do there. These three sine waves I'm taking 120-degree phase shifted into comparator resistor, and this TBPRD is there, okay, and I'm comparing this particular sine with this triangle, which is from I guess 0 to 2000. So my sine also has to have magnitude from 0 to 2000. That's why I have multiplied it by TPRD, and then I'm putting the logic into my code. That logic I have set it over here, that whenever my comparator is counting, is touching A on up count and is touching A on down count, I'm setting and clearing the pulse. So in this way also you can obtain. And B signal, if you want inverted of up signal, you just put clear and set opposite instruction to that. Okay. Then you can see I have assigned sync output of EPWM1 module at time base counter 0. It means my counter will start counting from 0 itself. And now rest of the PWM module, I have to put time-based sync in instruction. So this is the inherent the keyword. Okay, this time-based sync in is a keyword which will having be some macro expansion. What does this mean is that your synchronization flow will be continued. So once if you want to synchronize every module from 1, 2, 3, 4, 5, 6, you just put this instruction sync output selection equal to TB sync in. So with this instruction, you are able to synchronize all the modules together. Okay, so you can see in my every module that particular instruction will be there, sync output selection. Okay, so 4, 5, and 6, every module is synchronized with that particular instruction. And first module is synchronized to time-based counter 0. Like whenever my counter is starting to 0, okay, then after that point of time, I have told PWM module to turn its clock on, and other PWM's module will be there into the flow with this particular instruction. Okay, it just allows to pass through, you can say like that. Okay, so this is about that. I have selected deadband here also previously. These are the modes for selecting deadband. I have enabled deadband into active high complementary mode as EPWM 1A and 1B I wanted in complementary mode. Okay, and you can also put here bits. Okay, 0, 1, 1, 2, 2, 3, whatever values are there according to your which mode you want. Okay, we saw how to put that by using interrupts as well. So input mode, I'm selecting here DBA all means I want deadband into both the pulses, that is EPWM A and B as well. Then I'm putting rising edge delay and falling edge delay into EPWM 1. So that is of 200 here. That particular value is 200. So it's, I guess, into the nanoseconds. 200 nanoseconds of delay I'm giving into two pulses. So it's like that. So whenever what I'm doing exactly here is I'm putting comparators, sine values into comparators, and I'm that comparing that values with my triangle which is there with this TPRD. Okay, so till here does anybody has any doubt?